So today we have David Mehrle talking about free and complete Tambara functors that are almost never flat.
Thanks, Sarah, and thanks for organizing GROOT. I'm excited to give the very first GROOT talk, so hopefully I set a good precedent. Okay, so the title of my talk is Free and Complete Tambara Functors Are Almost Never Flat. This is the title of a forthcoming paper with J.D. Quigley and Mike Hill. I know we've been promising this for a while, but I think it's really true this time that it should be on the archive within a week. Okay, so I want you to contrast the title of this talk with the statement. With the statement that free algebras are always flat. So what does this mean? Well, if K is a commutative ring, then K adjoin X is the free algebra on a single generator. And as K modules, K adjoin X is isomorphic to K with the basis 1, X, X squared, X cubed, etc. And this is a free module with countably many generators. So therefore it is a flat module. Right? So this is really useful, for example, if you're trying to compute like a cotangent complex or something, or if you take a polynomial resolution of some algebra, and then you want to do homological algebra with it, you have this resolution by free algebras, and you want to know, are these suitable for homological algebra? Then the question that started us on this path is the following. What about equivariant algebra? So does the same thing hold equivariantly? And so I just want to draw some parallels between algebra as you know it and equivariant algebra to give you an idea of what we're really asking with this question. So here is algebra as you know it. And here is equivariant algebra. So here we might have an abelian group. The equivariant analog of this is a Mackey functor. You have the integer z. This is the Burnside Mackey functor, which is normally written as an underlined a. We might over here have commutative rings. And this is where things get a little weird. There are multiple options for the equivariant analog of a commutative ring. So we might have something called green functors, or we might have something called Tambara functors, or we might have something in between the two called incomplete Tambara functors. And all three of these things, well, really, their Tambara and green functors are special versions of incomplete Tambara functors. All of them correspond to commutative rings. So why are there different notions of this? Well, in algebra, a commutative ring is an algebra for the E-infinity operad, for the commutative operad, right? And a green functor is an E-infinity algebra in Mackey functors. But properly, there's more than one commutative operad in equivariant algebra. So these are called the n-infinity operads. So this is an n-infinity algebras in Mackey functors. So these are all like equivariant commutative operads. Sorry to squeeze that into the corner there. So so there's a lot more rich structure in the equivariant case. And then finally, there's the free algebra that we were talking about. Z, so this would be like Z adjoint X or something. And over here, we have a free incomplete Tambara functor, which we call A, O, X, G mod H. So classically, when you have a free algebra, you have to say only the ring, right, and a variable. But now we say more, right? We have to say which kind of ring we have. We have to say not just a commutative ring, but which kind of commutative ring. So this is, you have to specify an n-infinity operad, that's O. And then because we're equivariant, so there's a group floating around in the background, we have to specify how this group acts on the variable. So that's this subscript G mod H. Okay, so I guess I should specify that we are always thinking about a finite group G when we're talking about equivariant things. Okay, so this is all by way of introduction, but I want to state some theorems and then explain all of the ingredients and come back to these theorems at the end of the talk. So here's our first theorem. If G is a finite solvable group, then we give conditions on this operad O and the subgroup H such that the free incomplete Tambara functor, whatever this is flat. Right? So this is, we can give precise conditions that if you know the subgroup H and so this is H is a subgroup of G, and you know this operad, you can tell me yes or no, is your free algebra or free incomplete Tambara functor flat as a module. Okay, and then the second theorem is that in a precise sense that I hope to talk about later, this X G mod H is almost never flat. So as this operad O varies, and as the subgroup varies of subgroups of the group G, this I want to say something like with probability 0, if you pick one of these free incomplete Tambara functors at random, with probability 0, it's going to be flat, right? So almost never flat. Okay, so these are our two theorems, and okay, this is interesting. Maybe you want to do homological algebra with these things, but why do you really care? So what led us to this is that we wanted to do some calculations, right? So things like the Hill-Hopkins-Ravenel proof of Curvaire invariant 1 involves spectral sequences of Mackey functors. The homotopy groups of genuine equivariant ring spectra will give you various incomplete Tambara functors, right? So if you want to calculate with these things and do homological algebra or spectral sequences, you need to know some of the homological properties of these things. So that's what led us to this this theorem. Okay. So this is all by way of introduction. I hope to, throughout the talk, introduce the ingredients of this first theorem, but I really want to focus on the jump, or how you get the second theorem from the first one, because I think that involves some fun calculus. And we're all grad students, we know that all too well. And it's actually kind of elementary once you accept the first theorem. So I think that's kind of a fun result. Okay.
David, in the second theorem, is G also going to be finite, or do you allow it to be compactly?
No, sorry, G is always finite. So,
Okay,
yeah, this is finite G. But it may not be solvable.
Can I also ask a question about the second theorem?
Yes.
So when you say like with probability 0, is G moving as well, or is this just H and O that are varying?
G is moving as well. Yeah.
Okay.
And the precise statement involves a little bit of a setup, so I'll hope to get to that at the end.
Okay, thanks.
Yeah, thanks for the question. It is not precisely stated as is.
I'd also like to ask a question about that theorem. So the measure of Q inside R is 0, but somehow you can always approximate any irrational number by a rational number, right?
Right.
Is this almost never flatness of the same character, or is it completely different? Like, is close to any incomplete Tambara functor, can I find a flat one arbitrarily close to it?
Well, close is hard because these are both countable sets, right? Like the totality of finite groups with indexing system, or these operads and the subgroups, is countable, and so is the flat ones. So I don't know, but let me answer with a different approach. Is that you can localize these things. You can invert a single element. So even though they're almost never flat, you can invert a single element, and they will always be flat.
Fantastic, thanks.
So it's like all rational, like all yeah. Anyway, if you heard the statement all rational Mackey functors are free, it's kind of similar to that, but you don't invert all integers or something. Anyway, that's an interesting point, and maybe something I should think about. But yeah, thanks for the question. Other questions? Okay, well, I can't give a talk about Mackey functors and not tell you what a Mackey functor is, but this is not going to be the focus of the talk, so please excuse the brevity. Okay, so Mackey functors. So you'll say
I'm also wondering, like, if is like doesn't matter what H is in this theorem?
Yes.
What?
Or for which theorem?
Like the two above theorems. It is like is it still is it still like almost never flat, like even when H is like trivial?
Well, H is varying in that theorem. You'll see. You'll see.
Oh, H is like
I'll
very.
state these
Oh,
precisely
yeah, okay, yeah,
in
okay,
later in the
perfect,
talk.
thanks.
Yeah. Okay. A Mackey functor is an additive functor M from this category A, G to abelian groups. So AG is the Burnside category. It has objects, finite G sets, and morphisms. Okay, so the morphisms from X to Y is the group completion with respect to disjoint union of spans of finite G sets, right? So a typical element of this might be, well, so a span, you have X, you have Y, is some other thing here, some other, and equivariant maps F and G, or equivariant functions. And then composition of spans is pullback. So if you have X, you have Y, you have Z, and you have two spans here, okay, I'm not giving the morphism at the apex a name, then you take the pullback here and you get another span. So that's how you compose morphisms in there. And the direct sum in this Burnside category, so in AG, is the disjoint union of finite G sets. So that's what it means additive. It sends the disjoint, your Mackey functor M sends the disjoint union of finite G sets to a direct sum of abelian groups. Okay. But actually, lest you think that this is kind of a weird, complicated thing, Mackey functors are very concrete objects that you can work with. So notice that every object in this Burnside category is the disjoint union of its orbits. So these are things of the form G mod H for H less than or equal G, right? You can just decompose a finite set with an action of a group G into disjoint union of its orbits. And every morphism in this category is a composite of two morphisms. So TF, which is this span, and R sub F, which is this span. Right? So you can really reduce the total amount of data you need to say to give a Mackey functor, right? Like you don't need to say what it does on every finite G set. You only need to say what it does on the orbits. You don't need to say what it does on every morphism. You only need to say what it does on these R's and T's. So to define a Mackey functor, M, it suffices to give abelian groups M of G mod H for H a subgroup of G, restrictions, so restriction from H to K, and this goes from M of G mod H to M of G mod K, and transfers, transfer from K to H, goes from M G mod K to m g mod h. So these transfers correspond to the morphisms T, and restrictions correspond to the morphisms R, right? And of course, these data are subject to some conditions, which you can look up. This isn't important here. So I should give an example. So the Burnside Mackey functor A with an underline. So remember, if you remember the table from the beginning, this was the thing analogous to G, or to the integers Z. The Burnside Mackey functor has, so A of G mod H, we'll say that this is K0 of the category of finite G sets with disjoint union. And the restriction from H to K, well, this will just be a forgetful functor. So if you have the class of a finite H set, you can consider it as a finite K set for K, a subgroup of H. I don't know if I said that before. I guess I should say that K is a subgroup of H, is a subgroup of G. And the transfer from K to H of the class of a finite K set, X, is the class of the induction. So you take the product over K with X, and this turns a finite K set into a finite H set. So even more concretely, if G is CP, finite cyclic P group, then we can draw our Burnside Mackey functor like this. So this is Z plus Z. This is A of C2 mod C2, the trivial orbit. This is A of C2 mod E. This is Z down here. And then we'll have a transfer here. So this sends 1 goes to 0, comma 1. And over here we have a restriction, and this will send A comma B to A plus PB in there. And this is the restriction, right? So this is all of the data to specify a CP Mackey functor. Okay. So here's a theorem due to Lewis. It's two things. So first, the category of Mackey functors is abelian. And there is a symmetric monoidal product written alternatively just a box, or I prefer the box with an X through it, with unit the Burnside Mackey functor. So what does this mean for us?
Yeah, David, can you scroll up to the definition of the Burnside Mackey functor again?
Yes,
Oh, thanks.
right here.
Oh, okay. I think I got it now. Thanks. Right.
Cool. Other questions?
Just a comment. In the right side of the example, you wrote C2 instead of CP, right? That's just a typo.
Oh, thank you.
Yeah. The generators are the trivial action and the sort of cyclic action on a set, right? And
Yes.
then you have the C plus C. Yeah.
Yeah. So the two possible orbits are an element is either fixed by the CP action, or it has a whole.
Yeah, that makes sense.
CP. Yeah. Thank you. Okay, so the category of Mackey functors is abelian, and there is a symmetric monoidal product, which is written alternatively as just a box or a box times with unit A. So what does this mean? This means that it makes sense to do homological algebra in Mackey functors, and also free, projective, and flat Mackey functors make sense. Right, so for example, a flat Mackey functor is a Mackey functor such that taking the box product with it preserves short exact sequences. Okay. And then let me give you a little bit more. So since we have a box product, we can talk about monoids. So if a commutative ring is a monoid for the tensor product in the category of abelian groups, a green functor is a monoid for this box product. And what is this? Well, this is an E infinity algebra in Mackey functors. So like Mackey functors, you can concretely describe a green functor. So concretely, a green functor R is a Mackey functor such that each R of G mod H is a unidal commutative ring. And the restrictions is a ring homomorphism. Right. So it's a Mackey functor plus extra extra structure, right? Let me give an example here. So the Burnside Mackey functor is a green functor. Green is a person's name, so I guess I should capitalize it. So A of G mod H, if you recall, this is K0 of finite H sets with disjoint union. Well, the product here is the Cartesian product of finite H sets. And again, back to our G equals CP example, we can write a ring structure on this. So this becomes Z adjoined T mod class of, or mod T squared minus 2T, and Z down here. And then the transfer is multiplied by T, and the restriction is T maps to 2. So T is the class of CP. Oh geez, I'm getting exactly what I did above. T maps to P, T minus P, T squared minus PT.
Hey David, in your definition of green functor, there should also be a compatibility between the restriction and the transfer, right? In the multiplicative structure.
Yeah. I guess I also skipped this in
Okay,
definition of Mackey functor. I said subject to some conditions, so that's right. Subject to some conditions. Right, which, I mean, they're tedious to write down and they won't end up being important for our purposes. So, but thank you. Yes, that's important to say. Okay. Other questions? Okay. So so these green functors are the naive kind of things that happen when you use the E infinity operad in the category of Mackey functors. But really, you should have some sort of equivariant operad. So these are the N infinity operads. So we can say that an incomplete Tambara functor is an N infinity algebra in Mackey functors. So in a second, I'm going to switch gears and talk about these N infinity algebra or N infinity operads. But let me give you let me give you the concrete version. So for example, a Tambara functor is a green functor with the data of norms. So in addition to the transfer, if you think of the transfer as an additive kind of thing, you need the multiplicative kind of thing. So a norm. So this is the norm from K to H will go from R of G mod K to R of G mod H. And this will be a multiplicative homomorphism. By which I mean it's a homomorphism for multiplication, but not necessarily for addition. And the example that we've been going with is the Burnside functor. And this has norms. So the norm from K to H of a finite K set X, we'll say this is the class of the finite K set, finite H set from H to X. So what is this? So this is K equivariant functions from H to X. And it becomes an H set with the action on the domain. And then incomplete Tambara functors may have some, but not all norms. And these norms are parameterized by this N infinity operator. But the important thing is that the fact that it's an N infinity algebra, this gives a notion of free algebra, right? And these free algebras, these were the A, O, X, G mod H we saw before. Okay. So I'm going to switch gears in a second and talk about these N infinity operads. But if anyone has any questions before that. Okay. So how are these norms parameterized? How do we get these incomplete Tambara functors? So I'm going to start with a theorem due to, I think, Rubin, that says that N infinity operads are in bijection with indexing systems. And indexing systems are a very concrete categorical or concrete combinatorial object. So let's define an indexing system. An indexing system O is a suborder of the subset order on subgroups of G. So I guess this is more correctly an indexing system for your group G. And remember, G is a finite group here. So it's a suborder of this such that, well, first, okay, so I'm going to write my suborder as an arrow with a subscript O. And that means that, so I'm going to write it like this, K arrow H arrow O H. And this will mean that K is less than H in this order. So if K is less than H in this order and L is a subgroup of H, then K, L intersect K is less than H. And if K is less than H in this order and G is in G, then GK G inverse is less than GH G inverse. So it's conjugation invariant. So these are very concrete combinatorial objects. Let me do an example. So if G equals CP, oh, I sense a
Excuse me,
question
Dave.
coming. Yeah.
Yeah, I've got a quick question for you if you don't mind. So you're talking about n infinity operads here. And I know, for instance, in like those papers of Blumberg and Hill, they talk about n infinity operads, which are operads in G spectra or G spaces. So is what you're saying that there's some notion of n infinity operads in Mackey functors? Like you have like a sequence of Mackey functors that form an operad or something like that? I'm not sure if that question made sense.
Yes. I mean, I guess if you want to think about it in terms of like genuine equivariant spectra, right? So if you have an n infinity operad in genuine equivariant spectra, its pi 0 is going to be the corresponding kind of incomplete Tambara functor.
Okay, great. Thank you.
Yeah. Sure. Yeah, so let's think about G equals CP. So there are two systems here. So, well, we could have E and CP, and we could have no relation between them. So we'll call this the trivial indexing system. And then we could have E and CP, and we could have E is less than CP in this relation. And in fact, this is the entire subgroup containment order. So this we'll call the O complete, the complete indexing system. And in fact, I want to briefly switch and show you a bunch of indexing systems. So we're looking at these tables here, but I want you to ignore everything except this first column of the table. So this first column here, these are the indexing systems for CP squared. So this is CP squared systems, right? This first one is the trivial one. This last one is the complete one, but now there are 5 of them, right? And it's a fun exercise. You can work this out just from the definition of an indexing system. So then scrolling down, we can look at this next table. So this is the CP cubed systems. So again, we have the trivial one here, and we have complete one here, right? And there's a bunch of stuff in between. So this is what they look like. Again, this becomes a little tedious, but you can work it out from just the definition. And then here, CPQ, so for P and Q coprime, right? This is a picture of the subgroup lattice, and these are the valid suborders that become indexing systems. And then finally, if you want me to show a non-abelian group, here is a dihedral group, and you can again look at this first column. So H1, H2, and H3 are the 3 conjugate copies of C2 inside the dihedral group of order 6. And this C3 here, maybe I can zoom in. The C3 is the copy of, is the subgroup that is the cyclic of order 3 inside D6. And here are some indexing systems. I can show you some more of them. But yeah, so these are very, very kind of concrete combinatorial things that we can get our hands on. Okay. So I want to give you a theorem due to Balkin, Barnes, and Reutzheim. Says that they count, or they classify the ones for CP to the n. So the number of indexing systems for CP to the n is the Catalan number cat n plus 1, and this is 1 over n plus 2 times 2n plus 2, oops, not divided by, 2n plus 2 choose n plus 1. I think in general, it's an open question to enumerate or count these things for other groups. So maybe if you wanted to do dihedral groups, D2N, I think that's an open question. Or even cyclic groups like CPQ or CP1, P2, P3 or something like that. Okay. So if you remember, this is one of the two things that our free incomplete Tambara functor could depend on. So free incomplete Tambara functor. This will be A, it'll depend on our indexing system O, and then X G mod H. So this is our indexing system, and this H is a subgroup. So this is for G and H, subgroup of G. So, well, we computed, so let's go back to these tables. We computed a bunch of examples. And we're like, well, when is the thing underlying? So when is this free and complete Tambara functor free as a Mackey functor or flat as a Mackey functor? So the way you read one of these tables is that, so along the top here, this is your subgroup, or this is, yeah, this is the, this is G mod H along the top. So this is CP squared mod E, CP squared mod CP, or CP squared mod CP squared. And then along the left-hand column is the indexing system. And then in each square, the word free will appear. So this is free. This means that A O triv adjoint X CP squared mod CP squared is free as a Mackey functor. Right? So I want you to pay attention to the proportion of them that are free. So in this first table, so this is for CP, half of them are free, right? A lot fewer of them are free for CP squared. What is this, like 4 out of 15? For CP cubed, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 out of 14 times 4, right? And it only gets worse from there. But you can see that from these tables, it appears that as n increases, the proportion of free incomplete Tambara functors that are free as Mackey functors or flat as Mackey functors really decreases, right? So actually, let me give you the theorem that tells you exactly when this happens. So here is our theorem. Let G be a finite solvable group. Then the following are equivalent. So 1, this free incomplete Mackey functor is free incomplete Tambara functor, free as a Mackey functor. And if you're confused about the difference between free as an incomplete Tambara functor and free as a Mackey functor, this is like the difference between being free as an algebra, so k adjoint x, and free as a module. So k adjoint x, free as an algebra, has a single generator, but as a module, it has accountably many generators, 1, x, x squared, x cubed, and so on. So this says the free algebra is free as a Mackey functor. This is equivalent actually to this is flat. So if the underlying Mackey functor there is flat, that's equivalent to it being free. And the third condition is the useful one. So this says that H is normal in G. IH star of O is trivial. Let me explain that in a second. And H is less than G in this order. So what does this mean? IH star O is the intersection of O with the complete thing for H. So for example, let's say I had CP squared, something like this. So this is O, then ICP star O, this would be E to CP, right? You just take everything less than that, less than your subgroup. And that becomes your new indexing system. So it's an indexing system for a smaller group. So these are actually pretty concrete conditions on which, on the thing, right? You can look at your combinatorial suborder, right? You can look at your indexing system. You can say, is H less than G in this order? And are there no arrows from anything below H to H? And then if H is normal in G, that tells you your free and complete Tambara functor is flat as a Mackey functor and indeed free as a Mackey functor, right? And here's an interesting corollary. For each O, there is at most one H such that AO X G mod H is flat. So this third condition actually insists that H must be the minimal normal subgroup of G with an arrow, or sorry, that is less than G in your order, right? Alternatively, to construct H, you take everything in this order O that has an arrow to G, right? And you take the intersection of all of those. Then the conjugacy condition guarantees that it's normal. But in any case, for each O, there is at most one H, right? And this is why we can do any asymptotics here, right? This is why we can get our almost never statement, which I think is really cool. So let P of G be the number of pairs OH such that this X G mod H is flat, and T of G is the number of pairs OH in total, right? And for a fixed group G, we are interested in this ratio P of G over T of G, right? And this is equal to number of pairs OH, which yield a flat thing, divided by the total number of pairs, which is the number of indexing systems, O multiplied by the number of subgroups of G, right? Well, we have this corollary. For each O, there is at most one H, right? So the number of pairs which yield a flat thing is less than or equal to the number of indexing systems. And hence this ratio is less than or equal to 1 over the number of subgroups of G, right? So here's a theorem. The limit as n goes to infinity of the sum from I equals 1 to n of P of Cp to the I divided by the sum from I equals 1 to n of T of Cp to the I is 0. And here's the proof. This limit, okay, I'm just going to copy and paste. This is the advantage of not using a chalkboard. Okay, well, we don't know it's equal to 0 yet, but this is less than or equal to the limit, the lim's up as n goes to infinity of P of Cp to the n over T of Cp to the n, right? Which is less than or equal to the limit as n goes to infinity. So here we can apply this inequality, right? It's less than or equal to 1 over the number of subgroups. And the number of subgroups of Cp to the n is n plus 1, right? And this is 0. So if you're curious about this inequality here, right, I'm just going to say it's an exercise. It's elementary, but say that AI, BI are positive numbers, then the lemma is that the sum of AI divided by the sum of BI is less than or equal to the maximum of AI over BI. And then you get this inequality by taking the limits. But that's a fairly elementary analysis thing. Okay. So this is our theorem. This is the almost never. So this is the almost never theorem for Cp to the n, right? This is only for cyclic groups. And with a little bit more work, you can do this for all finite groups. So let me state that theorem, and then I'll give you the key ingredient, but we're not going to prove this because it's kind of fiddly. So the theorem is that fix a bijection, I'll call it blackboard bold G. This will be from the natural numbers to the set of all finite groups. Right, these are both countable sets, just pick a bijection. Then the limit as n goes to infinity of the sum from I equals 1 to n of P of G, G of I divided by the sum from I equals 1 to n of T of G of I is 0. So you should think about this as the ratio. So this, as n goes to infinity in the top, this is the number of things which are flat, right? The number of pairs of indexing system for G and subgroup. such that the free and complete Tambara functor with that indexing system in that subgroup is flat, and this is the total number of such things, right? So you should think about this ratio as number of things which are flat divided by number of free and complete Tambara functors that are flat divided by number of free and complete Tambara functors. And the key ingredient is a theorem of Kamina, Everest, and Gagan, which says that almost all finite groups are solvable. So once you reduce this to almost all finite groups are solvable, then you can apply this corollary here from our theorem, right? So our theorem requires G is a finite solvable group. And so the corollary does as well. But then you can use this inequality right here after reducing to the solvable case. Okay. And that's all I have. Happy to take your questions.
All right, let's take a moment to thank David. And any questions for the recording?
Yeah, I have a bit of a technical question about the statement of theorem 1, if that's fine.
Which one?
Sorry, the theorem about G solvable, the one, yeah.
Yeah, this one.
When you say free as a Mackey functor, do you mean direct sum of A's, or do you mean free with respect to the forgetful functors? And what is the connection between the two notions? And
right. Okay,
you
so
studied?
so free as a Mackey functor is not just a direct sum of A's, right?
Okay.
So as with the there are multiple choices of where you put your variable, where you put your generator, right? You could put your generator, you could say your generator has a trivial action, or let's think about CP. Your generator could have a trivial action, or your generator could have a could be in a cyclic orbit, right? And those give you two different kinds of free Mackey functors, and direct sums of those give you an arbitrary free one. To answer, I guess the categorical interpretation of this is that a free Mackey functor is a representable one. So a Mackey functor is a functor from this Burnside category to abelian groups. Representable functors have this Burnside category. So morphisms in the Burnside category from some finite G set to something gives a Mackey functor, and this is a free one.
Okay, thanks.
Yeah, of course.
I had a question.
Yeah.
So when you showed these tables, it seemed like, you know, the table wasn't just getting sparser in terms of area, but maybe as the groups grew bigger, there were also more gaps vertically.
Right.
Is this something you've investigated? Like, as in the statement you're making about these functors like being almost never flat, do you think that could be strengthened to saying almost no indexing systems admit a free Mackey functor, or is there like a counter example, or you know?
So actually, I have to say that this is something that we want to follow up with, that we haven't thought about much yet. Yeah, because it seems kind of like we can make two extremal statements, right? Like the upper right and the lower left of one of these tables is always going to be underlying free, and then we kind of reduce everything to one of these other two cases to prove our theorem. And yeah, I feel like there's a lot more room to say more things about this, because I mean, I suppose by just looking at your indexing system and saying, well, something like this one, right? If you take CP squared, you want it to be free on something at CP squared. Well, everything below that should have no arrows into CP squared, right? That's the IH star equals O triv condition. Well, that's not going to happen, nor is it going to happen with CP, right? So you can never have anything there in this row of the table. And there are a lot of indexing systems like that. Yeah. I mean, another interesting phenomenon is when you go to the non-abelian thing, right? There are these whole three columns for the dihedral group. These whole three columns. I mean, those aren't normal subgroups, right? So those columns are just totally empty. So this one's pretty sparse. And I don't know enough finite group theory, but I would imagine that groups have don't have a lot of normal subgroups, right?
But aren't they conjugate to each other? These three subgroups?
Yeah, they
They're the
are.
two different. So if
So these three
I'm a
columns
little
are
confused
really
because your
different.
indexing system has a symmetry under conjugation,
Mm-hmm.
and your the value you take your functor on, like or the variable you join, does not have this conjugation symmetry in a sense. So it seems like if you have a number of columns that are related by conjugation, you could never have a free Mackey functor there, because otherwise that would break your corollary, right?
Right. So what you said, the variable only depends on the orbit, right? And if subgroups are conjugate, they'll give the same orbits. Like if H and K are conjugate, then G mod H and G mod K will be the same orbit. So there is a symmetry on orbits there.
I'm confused about this example, but thank you.
Yeah, sorry, I couldn't clarify more.
Thanks.
David, I had a question.
Yeah.
First of all, thanks for your talk. I think these results are really cool. Second of all, I was wondering if many or any of these results can extend to answer the question of whether or not many free R algebras are flat, where R is some other green or Tambara or incomplete Tambara functor.
Right. So let's go back to this theorem. G is a finite solvable group. Let's say that you want, instead of the Burnside thing, you want some other R, right? If you erase the A's and replace them in R's, this theorem is the same.
Really?
And the reason for that is that the kind of change of base functor, so like box product with R over A,
right,
that preserves free, flat, and projective things.
I see. And then you're just using the fact that the free R algebra is just R tensored with.
Yeah. So R O X G mod H is the same as R box times A O.
Gotcha. Well, thank you very much. I actually have to head out right now, but I appreciate you answering my question.
Yeah, of course. Thank you.
Thanks, David.
So I was wondering if from this there are any computational examples which seem more tangible, or like now that you know that some things are free as Mackey functors, then like are there a few examples that you particularly want to do a computation with, or is that just totally different flavor so you're not thinking about it?
Well, now that we have this, let me tell you how we came to this, right?
Okay.
So if you want to compute a cotangent complex of something, right? Cotangent complex of some K algebra relative to K. You first resolve by polynomial algebras. So you come up with this crazy resolution by polynomial algebras. And then you take a tensor with it and compute some homology. right? But this only really works because when you take a resolution by polynomial algebras, they're also free as modules, right? So this resolution of algebras is actually also a free resolution of modules. And so we were led to this because we were thinking about cotangent complexes of Mackey functors and stuff. I guess Mike Hill has a cool paper that's Andre Quillen. It's like on the Andre Quillen homology of Tambara functors, and other people have done similar things. And we wanted to do some of these computations or think about a cotangent complex. And well, I don't know if you've seen that recent XKCD comic that was like the 10 types of, or like 12 types of scientific paper. This one is, that other problem was hard and we needed to solve this one first. That's what this result is, yeah.
Yeah, that makes sense. So I guess with this, it's still hard to do the other problem though, because you don't have as much freeness as you would hope for.
Yeah, we haven't really gone back to it yet.
Okay.
But I think it should be doable. Yeah, so we have this other theorem as well, which will be in the same paper, that says after you localize, then all of this weirdness goes away. After you can invert a single element in the Burnside functor, and then every free incomplete Tambara functor over this, like localized version, will now be flat underlying.
Okay.
So
You have a way to get to a world where things are much more computable.
yeah, exactly.
Okay, cool.
So not all is lost.
Yep, very cool. Thanks. Any other questions? All right.
Yeah, I
Well,
actually have another one,
yeah.
if that's okay.
Yeah, absolutely.
So you were led to these theorems, as you said, for computations, but it's still, you may still wonder if there is like a derived or a spectral analog. So flatness makes sense because you have a T structure, or maybe several T structures. So maybe, or yeah. Did you ask this question derived or spectrally, and if so, what's the answer, if you know it?
Well, we have not. I feel like that's something that I wrote down would be an interesting thing to think about, but we haven't gone there yet, and I don't know.
Okay.
That's a really good question, but I don't know.
Okay. Thanks for the talk, by the way. It was really nice.
Of course, thank you.
You made this comment earlier about how many groups have non-normal subgroups, and I don't know if we can make this precise. As in, I guess it would be reasonable to assume that most groups have that most of the subgroups are not normal, right?
Yeah, that's what I'm saying, but
whatever those words mean.
Yeah, whatever that means. I feel like I can't make this precise, and I was more idly speculating than making a statement.
Well, if there are perhaps no further questions, I'd like to thank David again for the great talk.